Afternoon and good evening to our participants from Europe, the US, and Australia. And welcome to the Forecasting One session of the ESIG 2020 Meteorology and Market Design for Grid Services Workshop, being held online on Tuesdays and Thursdays during the month of June. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As most of you know, we were originally planning to do our annual Forecasting and Markets Workshop in Denver this month, but due to the coronavirus situation, we found it necessary to move the workshop online. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and co-chaired by Julia Matoy-Basan of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who make ESIG what it is, and we encourage you to become members and get involved if you're not already. Regarding logistics, I would ask you to note that the webinar will be an hour long. We'll have 3 individual presentations, and we plan to hold the questions for a 15-minute Q&A session after the last speaker. So please keep the questions coming during the presentations, and we'll address them at the end. Recognizing the limitations of a webinar with 100 or more people on the lines will be muted, so we ask you to use the question box in the lower right-hand corner of your screen to submit your questions. Today we're hosting the Forecasting One session, Solar and Wind Forecasting R&D Project Updates, chaired by Tassos Golnas of DOE, with Eric Grimit of Vaisala serving as the co-chair. Tassos manages the solar PV forecasting program at DOE and has been there since 2016. He has a background in PV system modeling, monitoring, performance, and reliability. Eric is the head of an applied research team with a focus on weather-related decision support at Vaisala and is an internationally recognized expert on forecasting for renewable power generation. Tassos will manage the session logistics and do a presentation, and Eric will handle the Q&A. I've known both Tassos and Eric for some time now and consider them both good friends. Tassos and Eric, we appreciate having you here, and I'll now turn it over to you, Tassos.
Charlie, thank you for the kind introduction and the privilege to chair this session and the opportunity to share the current status of DOE solar forecasting program, along with some words about the near future. So I'll begin with a slide about CETO and what we're about. Right? So it's all about improving the affordability, performance, and value of solar technology on the grid. And you can see how we do it by advancing solar technology in national labs as well as academia and industry, enabling solar to support grid reliability, and providing objective technical information to stakeholders across the nation. And here's a slide from the team I work for, it's a systems integration subprogram, which shows the vision that we have for the grid of the future. A grid where power flows bidirectionally, where solar generation is found on both the bulk power and the distribution systems. Power sources are interconnected via electrical and communication pathways. Energy and power transactions can happen in open and well-regulated marketplaces, and power, information, and monetary flows are all kept secret. Now, forecasting, one of our core areas of interest, because we know that variability and uncertainty of generation, they raise the cost of integration of solar into the grid. So we see forecasting as a means to minimize the uncertainty and then let variability be dealt with technical and policy needs. In this space, we're currently funding 8 projects from the 4 that was announced back in 2016. The project kicked off in the summer of 2018. And we had 3 topic areas in the fall. The first one was about better evaluation of solar forecasts, whether those of irradiance or power. The second topic area was about improvement of the solar radiation forecast itself in intraday and day-ahead horizons, where we focus mostly on NWP models, despite what the picture tells you here, and a special emphasis on challenging conditions such as intermediate clearness index, and lamps. The third topic area focused on leveraging probabilistic power forecasts to improve the calculation of reserve generation. This effort called for close collaboration with balancing authorities, and you'll be able to see that as I describe projects in that area in a few slides. So we'll start with topic area 1. The University of Arizona is the lead team here. Will Holmgren is the PI. And they went on to deliver a common test framework that will allow the validation of focus models in an accessible, repeatable, and auditable manner. The teams have just released an advanced beta version of an open source framework that implements those objective and consistent evaluation scenarios and methods. So it's able to standardize the evaluation and thereby reduce the user costs and the provider costs for running those trials. It will help increase confidence in solar forecasts with the users, and that will allow a faster integration into the energy systems. And last but not least, it's a framework that's extensible easily to green power and load forecasting. The team will publish the first release candidate in the platform in the next few weeks. An advanced beta has already been out there for some time. And that version will be used to evaluate the models developed by the teams in topic area teams 2 and 3 during the final phase of their projects. Equally importantly, can generate reports which compare forecast observations or other forecasts across a number of well-documented metrics. Of course, users can use their own private observations or forecasts as a baseline data. Now, the team plans to run a forecast trial with real data and is soliciting users among the end user and forecast provider communities. So if you're interested, please contact Will at the email on the screen to learn additional details. Finally, in the image, you can see the locations for which the arbiter contains observations and forecasts of irradiance and power. If you participate in a trial in any of those, you can use any of those sites, or obviously you can choose your own site for which you can generate the appropriate data. Now let's move on to topic area 2. That's where we support 4 projects, and 2 of them are focusing on improving the microphysics employed by our state-of-the-art numerical weather prediction model, WRF-Solar, was developed by a team at Engerer during the first solar forecasting call back in 2015. The other 2 are also following different techniques for improving solar forecasting. I'll talk about that shortly. So first, the team at Brookhaven National Laboratory, led by Dr. Liu, is trying to improve the performance of WRF-Solar under cloudy conditions using microphysics parametrizations that were developed under climate-related research that was performed previously at Brookhaven. The parametrization of these certain physical processes is necessary in numerical weather prediction models, where the grid is too coarse due to computational limitations for those processes to be explicitly modeled. Unfortunately, many critical processes around forecasting irradiance are this kind of subgrid or fast physics processes, and that's why parameterization is really critical. As you can see from those plots, the team is experimenting with a number of parameterizations. They are shown here in colored bars and are compared to the baseline from WRF-Solar version 1, which is the gray bar in the beginning of each of those bar plots. And what we see is that there's definitely improvement in many of the quantities that are being predicted, are being estimated by WRF-Solar. And we have still 1 year to make these values even better. Another team, now led by Dr. Berg, Larry Berg at PNNL, with Engerer, Vaisala, and NOAA helping out, is experimenting with parameterizations for cloud microphysics too, but they have also been working to describe the relationship between cloud fraction, cloud type, and shortwave radiation variability using machine learning techniques. Additionally, the team is working on methods to quantify the effect of absorbing aerosols, such as black carbon, on the radiative transfer, and we'll implement them in a modified version of WRF-Solar. As I mentioned, the other two projects take different paths towards forecast improvement. We'll start with the project from NREL, with the help from Engerer. Manager Sengupta is the PI here. This project is creating ensemble members by perturbing the most sensitive input variables for each of the 6 modules that comprise WRF-Solar version 1. This ensemble mean forecast shows lower bias compared to the deterministic WRF-Solar version 1 forecast. And you can see on the slide, you can see the observation on the top left from the NSRDB data. And on the top right, you see the baseline WRF-Solar forecast. And the bottom right, you see the ensemble mean of the stochastically perturbed members and how it captures the conditions in the Midwest and the Mid-Atlantic regions better than the baseline model. Again, we have a full year to achieve even better performance in this model. Last but not least is a project led by Carlos Coimbra out of UCSD with Clean Power Research as a partner. The project is developing a framework that will allow the generation of probabilistic forecasts from a combination of models, some physics-based, some machine learning-based, whose parameters are optimized adaptively. Now, the project has had great success in using GO16 data to estimate ground irradiance based on a convolutional neural network technique. But it has also succeeded in demonstrating the accretive effect of adaptive optimization on the intraday forecast of GHI. In the image, the darker dots, and I know you have to squint to see the lighter colored dots, but just believe me in my description here. So the darker dots represent the bias and skill of the optimized algorithm for a horizon that goes from 1 to 5 hours ahead. The lighter dots represent the unoptimized results, and you can see in the tables the change in skill and bias that was caused by the adaptive optimization. These are preliminary results, and the project is about to hit their third and final year of performance. Now, in topic area 3, we funded 3 projects, and they explore different methods to calculate reserves and schedule and dispatch generation units in balancing areas that have high solar penetration. What's more, we asked them to do that by using information from probabilistic power forecasts that they will have to develop in the course of the project. The end goal is to grow the confidence of system operators in the reliability and the cost efficiency of the probabilistic forecasts, and also offer them a blueprint of a method that reduces the probabilistic input into a deterministic unit scheduling decision. On this screen, you see a comparison of methodologies that can be used to operate a power system with uncertainty, and I'd like to thank Aidan Tui from EPRI for supplying this plot. Now, the dynamic reserve calculation that you see on the far right is an important target for all the projects that I'm going to cover. So Aidan is leading the EPRI project with UL and Regina Tech as partners, along with HICO, Southern Company, and Duke Energy as utility partners. So far, the project has developed and delivered probabilistic forecasts. They're now designing use cases using detailed simulation of power system operations, and they will develop a platform that will take the forecast as input and generate scheduling decisions. What you see on the image on the right is a methodology used by the team to generate individual scenarios from a probabilistic forecast, while ensuring that the ensemble that you see on the right on chart B there, it has the same statistical properties as the original probabilistic forecast. These scenarios then can be fed individually to a reserve calculation tool, but they can also capture ramping requirements that underlie the particular distribution. Next up is a project led by Brian Matthias Hobbs at NREL, with partners at Maxar, UT Dallas, and ERCOT. And the project seeks to develop probabilistic forecasts for ERCOT and also create adaptive algorithms to calculate the reserves and perform economic dispatch. Thanks to the partner Maxar, the probabilistic forecasts are already being provided to ERCOT for all utilities scale solar plants in eco territory. And on the right, you can see the reduction in the hourly average non-spinning reserve requirement at airport that can ensue with the help of these algorithms that were developed by the team. In addition, the team has developed SolarView, which is a situational awareness tool based on a wind-related product, and it's approaching beta testing stage. I will close with a project led by Ben Hobbs of Johns Hopkins University, with partners at IBM, NREL, University of Texas, Dallas, CAISO, and MISO. Now, this is a massive project tackling multiple themes around data simulation, probabilistic forecast generation, ramp uncertainty, ramp requirement calculation, operational cost and reliability estimation, as well as operations work visualization. However, even though the team has made progress along every one of those vectors I mentioned, I'd like to underline some parts of the approach that's been taken by the team in their endeavor to develop this procurement solution for dynamic reserves that uses probabilistic forecast and that ISOs can do. More specifically, I want to draw attention to the lengths the team went to identify and understand the intricacies and peculiarities and sensitivities for each of the two partners with respect to result calculation and procurement, as well as to tailor the products to match the needs of the ISOs in question. So when we design these finding opportunities, we have a sequence of horizons in mind, starting from the one at the end of the project to those that extend all the way up to a decade. And the goal there is to inspire proposals that can move the needle not just in the near term, but ideally help nudge the whole industry towards a better future. As you can see, all the teams have made substantial progress, but the next 12 to 18 months is where we hope to see the culmination of the efforts and the delivery of significant capability in the applied energy space. At this point, I'd like to spend a few minutes to discuss what's coming up and what the community is thinking about the future challenges in this space. First, we have a fallout on the street, for which full applications are due next week, so I will not be able to answer any questions about that. I'll have an email address to which you can direct any questions you may have. Among the topics we have included there's one dedicated to the use of AI and machine learning in solar industry applications. And among the many example applications we have listed in the topic, two that have received a high number of proposals are long-term insolation forecasting, that's 4+ days, as well as achieving parity of net load forecasting forecasting with gross load forecasting, meaning targeting 2% hourly made for the ahead forecasts.
Hey, Tassos, time to wrap up. Thanks.
Thank you. So back in October, we held the first annual review of the solar forecasting program, and based on the discussions we had, we issued an RFI that was publicized in February, and by the beginning of March, we had a great number of very interesting responses. They covered many of the aspects I have itemized here for your benefit. I'd love to discuss them if you have particular questions, but right now I have to cede the floor to the next speaker. Thank you. So I'm going to wear my chair hat for the moment, and I'm going to introduce Rodrigo Silva. With a recently defended PhD, Rodrigo is now working in various research topics like solar, electric mobility, and even soccer analytics. His next goal is to pursue a postdoc outside of Portugal after this COVID-19 situation settles down, something we all look forward to. And I want to mention that the newly minted doctor, even though, like myself, it's a doctor that cannot save people, he did his PhD on spatiotemporal solar forecasting. So, very good choice to give us an overview of the value of solar forecasting. Rodrigo, please take it up.
Okay, so thank you, Tassos, for the introduction, and it's a real pleasure to be here and talk a little bit about the value of solar forecasting. So, to first create some common ground, I would like to start noting that solar generation is inherently variable in time, and whenever we try to predict it, there's always some degree of uncertainty involved. And while it's quite common to hear about the challenge of integrating the variable renewables, a PV integration study done by Eric L. et al. In 2013 by NREL estimated that 2/3 of PV-driven imbalance were actually caused by forecasting errors. And so why did I decide to address this value thing in specific? So after a 5-year-long PhD on solar forecasting, I found myself having read a bunch of scientific papers that either discussed the models, the data sources, or either the performance metrics on solar forecasting. However, whenever they talked about the actual purpose of the forecast, it usually would be summarized in a single short paragraph, and its end value would barely be addressed. And that's exactly what I want to cover with this presentation. And so when we consider a smart grid kind of layout, we can identify different and various end users for solar forecasts. And my first example corresponds to the solar plant operators, where when and for example, the case that I got here is that whenever a producer participates in the energy market, he is expected to provide at least once a day the forecast of his expected PV generation. And while the specifics vary from market to market, in all cases, penalties are applied to forecast deviations. And back in 2017, Antonanzas et al. Published a paper where they evaluated the relationship between the forecasting accuracy and the economic penalties of a 2-megawatt PV plant in Spain that participated in the Iberian day-ahead market. And this figure over here compiles the results of the paper, and on the x-axis we can see the normalized root mean squared error of a bunch of different models that they tested, and on the y-axis the economic value of each forecasting model. And so from this figure here, 3 conclusions can be made. The first one is that the value of the forecast seems to be linearly correlated with its accuracy. With a 1% improvement in the accuracy, increasing the value of PV generation by around 11 euro cents. The second conclusion is that state-of-the-art models still show great room for improvement. And the last conclusion is that perfect forecasts can save up to around 3.5 euros per megawatts and increase revenues by 10%. So when we move all the way up in the power grid hierarchy to the grid operators, we start talking about the actors that actually have to deal with solar uncertainty. And to do so, they usually use a set of uncertainty mitigation tools, which can be the ramping of generators, where their power output is requested to change, the dispatch of operating reserves, or, for example, curtailment. And each of these solutions makes grid operation more expensive. And so a paper by Martinez Anido et al. In 2016 simulated the power grid in the New England region in the USA, and they estimated that better forecasts could minimize the need for such costly solutions and reduce operation costs by up to $1.50 per megawatt hour. Because I initially thought that time would be an issue, I briefly listed on this slide here a bunch of other applications that can benefit from better solar forecasts. So for solar plant operators, we can have the scheduling of storage and curtailment for ramp rate compliance, and a reference for this would be Series et al. From 2019. There's also the thermal control of concentrated solar power plants, and with a reference from Nuri et al. From this year, so very recent. And regarding grid operation, better forecasts enable the deployment of cost-optimal strategies to cope with extreme events, being one of the examples, a solar eclipse and a reference from Killinger in 2016. Last but not least, in terms of prosumerism, forecasts can improve the self-consumption ratio by better allowing prosumers to better coordinate their load or their storage to their PV generation. In terms of final remarks, I hope that this presentation, which ended up being more shorter than I expected, clearly, or at least clearly highlights the broad range of applications that come up whenever solar forecasting value is addressed, and that it's difficult to compare the different applications or even the same application but in different contexts, because regulations, for example, dominate the implications of a better or worse forecast. And so the value of solar forecasting is found to derive from enabling a better scheduling of generators, storage, and load, and minimize grid imbalance. And as the behind-the-meter PV grows, a larger demand for net load forecasting is to be expected. The last point I'd like to make is on the importance, but also the challenge of including the cost of forecasting in these kind of assessments, since usually companies are very closed about it. And for example, from a broad range of references that I've read, only the reference from Series et al. Actually attempted to estimate these costs. So this usually would be my final slide, but because I still have a few minutes, if it's okay, I'll take the opportunity to explore some extra slides. And so here I'd like to refer to this very cool light reading article from Renewable Energy World from Stephen Natanz from 2014, where it's addressed exactly the potential that forecast brings in order to reduce and optimize the use of the costly solutions such as gas storage and, for example, grid interconnection. I want to actually skip these ones, but I'd like to end up with this really cool, let's call it landscape of the most extreme use case that we can find for solar forecasting, that is the solar eclipse. So for example, in 2015, the German grid operators had to deal with the loss of around 20 gigawatt hour. They had to deal with a 14 gigawatt dip in solar production, which after the eclipse actually led to a 25 gigawatt surge. And the most extreme ramping that they found was 700 megawatts per minute. And while this might appear to be extreme and completely unmanageable, the fact that the eclipse is perfectly forecastable and with a great time ahead, the operators were able to perfectly cope with this event and nothing actually happened. So no issues at all came up in the German power grid. And so coming up again to the final remarks, I'd like to thank you guys for listening, and I'm open to any questions or remarks. Thanks.
Thanks, Rodrigo. Eric, if we have, I think we have about 5-6 minutes left. If there are questions for Rodrigo, let's hear them.
Yes, we have a couple questions coming in for you, Rodrigo. One question is about solar forecasting verification. So you described some nice literature review on the value of solar forecasting. Did you do some validation yourself in your research, and where did you choose to get information from to do that validation?
Yeah, so well, just like the initial literature that I mentioned, most of my PhD and my research was focused on the modeling, what kind of data, what kind of forecasting approach, but never really in a real application context. And I would assume, because I have no experience with it, that it's a far more challenging issue since it brings the need to understand and be able to model applications such as energy markets, grid operation, etc. And so, no, I have no research done in this field. So the goal for me with this work was actually, because so I found out that there's already quite a few literature that addresses this value issue, but most of reviews and most of forecasting articles seem to dismiss a bit on this topic. And so this is, we can call it like a literature review. And I would say that the most common source that I found for this kind of literature is places like NREL, where grid integration, well, renewable integration studies are quite common, and I would say they have the knowledge and the tools to properly do so. I can also refer that in the end of this presentation, which later on will be made available, I put all the references that I have mentioned throughout the presentation.
Okay, maybe actually we could open this question up to any of our speakers here. Derek asks, what are some of the major sources of historical irradiance data for solar forecasting verification?
Eric, can you please repeat the question?
Sure, I'll repeat. So Derek is asking, what are some major sources of historical irradiance data, like in the public domain, for solar forecasting verification?
Yes, so the Solar Forecast Arbiter has amassed a good number of high-quality sources for irradiance observations, and they can be accessed by the, if you go into the Solar Forecast Arbiter website. They include not just the 7 SOLRAD stations, but I think dozens in addition to that. Again, they're all vetted and their data are ingested into the arbiter, so the forecast can be validated using irradiance forecast can be validated using those stations. They have also added recently a number, I would say about a dozen power observations from PV systems that are operated either by national labs or by University of Oregon. And we're always trying to add to that list of sites that can share publicly their power output, so that power forecast can be validated as well. Again, please head to the solarforecastarbiter.org website. The address is on my slides, and you can peruse through a large number of those observation locations.
Thanks, Tassos. For Rodrigo, we have more of a point than a question, but maybe we can rephrase this into a question. Rui Pestana points out that the solar eclipse is forecast, but it's not usually in our numerical weather prediction or NWP models. Did you look into this at all in your example, and what do you think should or shouldn't be included as far as solar eclipse in a standard solar forecast?
Yeah, so what I would comment is that, so besides the Killinger reference that I have cited here in this work, there's also a very interesting work by John Zach regarding, if I'm not mistaken, the American eclipse. And so I'm not sure in the details if it's an NWP model or not. So although it's not numerical, so it's not weather that we're talking about when it's about forecast, the fact is that an eclipse being non-weather, creates massive ramps and creates a massive loss of energy. And so in the same way as weather poses a great challenge for solar integration. So although it's parallel to the weather topic, I would say it's in line with the forecast value and integration like kind of idea.
Thanks, Rodrigo. And with this, we can end the question answer session and move on to the next presentation. Now I have the opportunity and the pleasure to introduce Dr. Nick Engerer, who is the CTO and founder of Solcast, a global solar irradiance and power forecasting data company that's dedicated to helping all of us build a solar-powered future. Nick holds a PhD in solar radiation modeling and forecasting and has managed a portfolio of $6 million in applied R&D funding, focused on bridging the gap between science and technology. Let's take it up.
Tassos, thank you so much for that kind introduction. And hello, everyone. It is morning time in Australia. You'll notice, thank you, coronavirus, I'm presenting from my car. That's to keep my family asleep in their beds in the house and not make too much noise. But you'll get to have a little bit of a unique flavor where we're all speaking from our homes. I'm from my car. There we go. So today, I'm going to talk to you about the progress that we've made in short-term solar energy nowcasting for large-scale solar sites. I'll give you a bit of an overview on how the technology works and also the motivation for the specific problem that we're solving. And it follows on really nicely with what Rodrigo was just discussing in terms of the savings and the benefit that solar forecasting can provide. And so the actually being located in Australia, our company was formed in Australia. We are a global company, but we work primarily on the very short-term forecasting for solar energy markets in Australia. And that's because it comes with a unique motivation and challenge in the energy market. So one of the things that happens in Australia that's slightly different than the United States, for example, is there's actually a 5-minute ahead spot market that's used for settlement of the supply and demand that is happening in a more fluid sense, the short-term sense. And that 5-minute ahead market has become more important as the amount of renewables in the electricity network has risen. And this 5-minute ahead forecasting requires that renewable generators set a dispatch target that they provide to the energy market operator, Australian energy market operator, AEMO. And this dispatch target is actually set every 5 minutes, as we see in this graphic here on the right. And the interesting thing about setting that target and the actual generation is that the actual generation might not meet that target at 5 minutes ahead. So you set this target as a forecast. It's a solar forecast in the case of a solar farm. And the generation may also vary in between the straight line between those dispatch targets over about the 4-second interval on which the ancillary service market operates. And its purpose is primarily to balance frequency, but it's being increasingly relied on to handle the actual forecasting errors that we get from renewable energy generation primarily. And the financial penalty that comes along with this is that there's a cause or pays factor that is calculated according to these errors. And they're binned up every 5 minutes, but they're calculated by this instantaneous difference every 4 seconds. And when that total cost of all the FCAS that was needed to correct for all the errors and all the frequency changes on the market across an entire region are summed up per month, a renewable energy generator will pay a percentage of that penalty according to their total FCAS requirements as a proportion of the total. And that cause or pays factors refers directly to that cost that they pay. It's quite detailed, and you can look up some great articles on a local Australian website called Watt Clarity if you're interested to dig a little bit deeper. But the main thing here is that the cause or pays factors, it's actually not uncommon for $100,000 per month total costs to being added to the operational expenditure, or OPEX, as I've abbreviated at the top of the slide, for utility scale solar sites. And so this is, of course, a massive amount of money to have come out of your operational expenditure as a solar farm. So what happens now in the status quo is that the Australian Solar Energy Forecasting System makes the dispatch target forecast for the utility scale solar sites. The problem with this is that while this solar forecasting system is actually, a respectable system in its own right in terms of how it operates over all time scales, at the 5-minute ahead dispatch forecast, it actually operates as a simple regressive model. And the challenge with regressive models, the one thing about them that has always been really apparent to myself as a previous researcher in this space is that they are in fact regressive. How will they predict the future if they're always using the past as its information? And because of the relatively simple approach that this utilized, we actually saw some very systematic problems with the forecast it was producing. And the response to that has been several projects that have been funded by our DOE equivalent. I'll introduce that in the next slide. But we did some work back in 2017 with our partner, Jonathan Dyson, at Greenview Strategic Consulting. And we saw that this difference between what we were able to forecast with a new technology, which I'll also introduce, versus what we were seeing with this regressive model, offered some real opportunity for improvement, even back in 2017. But what happened in 2018 is actually we had our Australian Renewable Energy Agency, basically the equivalent of CEDO at the DOE, but also including all renewables, not just solar, issue a funding round to go into this space and interact with a newly available system that would accept third-party forecasts into the energy market. It's an API that's been put up and supported by AEMO. And in our portion of this project, in our funding, we actually had 8 solar farms participate in our project and received $780,000 of support from the Australian Renewable Energy Agency. And you can read a bit more about that at this link. What we've done with that is we've actually taken a forecasting product that we refer to as Super Rapid Update as the product name. That name comes from the fact that Rapid Update are our normal forecasts, meaning that we're updating the forecast 0 to 7 days ahead every 5 to 15 minutes around the world. With the Super Rapid Update product, we're actually doing that every few tens of seconds. And so this forecasting product uses 3 key inputs. It has satellite-based nowcasting from the HIMAWARI 8 weather satellite, in this case here in Australia, which updates every 10 minutes at 1 kilometer resolution. We get a real-time data power feed from the SCADA system, which is updated every 15 seconds continuously. And we have sky imagers installed locally on site. And so what the technology does is it actually fuses all 3 of these sources of information to produce an instantaneous 5-minute ahead dispatch forecast for the solar farm site. So this satellite nowcasting is something we operate all around the world. It's a standardized product. And what it does is it's looking at the clouds every 5 minutes, in this case of the GO-16 satellite, and tracking them, detecting them, characterizing them, and forecasting them over the short-term horizon, not just in a single case, but a probabilistic case. So we got an example of a 0 to 2 hour ahead probabilistic ensemble forecast there on the right. So this technology is the starting point. We can use this plus the SCADA data to produce a fairly accurate forecast. I'll show you that in the end of the presentation, the cost-benefit analysis where that sits. And then we've also integrated with these cool little units called the Bloom Sky Sky Imagers. So we've partnered with this company, Bloom Sky, to basically access a weather station sky imager tool that we've now modified slightly with them through partnership to produce forecasts for solar farms that has been imaging the sky at a relatively low cost for almost the better part of a decade, really. And what we've done with the algorithms here is, of course, produced a HDR-based image that has optical flow type forecasts in it. I did actually have a video here I wanted to show you. I'm sorry that it didn't actually work out, that the file was too large for me to share. But what you would see in this image is, of course, the clouds being predicted where they're going to go next by these tiny blue vectors and whether or not they will occlude the sun. So these 3 pieces of information have been fused together to make these dispatch forecasts. We have a total of 18 operational sites now across Australia. And in this project, I mentioned there were 8 sites. That was kind of our starting point of the 8 different sites. And we have 4 different partners you'll recognize in the project: Edify Energy, Neoen, First Solar, and FRV. And these partners have provided access to that real-time SCADA feed and also work with us to submit those forecasts to the Australian Energy Market Operator API. Now, one of the things that I wanted to try to do for you, and on the left-hand side here, is give you some indication of forecast performance. We have these states here: New South Wales, Victoria, and Queensland. Let me just go back. Queensland, which is up here, the northern part of Australia. Up here's where all the crocodiles are. New South Wales and Victoria. So we can see that as we're moving to the north, we're getting into more tropical convective climates. And as you move to the south, more temperate mid-latitude climates. That's the opposite of the United States. I know you get used to it after a while. What we've seen in terms of looking across these sites is a general trend toward less predictability, poorer forecast performance in Queensland, where there's more convective activity, and better performance in the mid-latitude, more temperate climates. This outlier here is actually the Moree solar farm, where we've seen more improvement on the ACEP's model with our approach. That is our longest running site, and it's got the most mature, best machine learning on it. It's had a lot of experience. So there's also a tendency to have this accuracy shift upward in performance to the right in the image as things operate over time. It's difficult to draw a lot of conclusions to look at this spatiotemporally and across climates, but those are the general observations we have at this stage. And zooming in a bit more detail to that Moree site, this is a calculation from early 2019 comparing our forecast versus ACEP's in terms of the running sum of total errors. And then we can look at the distribution of those errors here on the right. A little bit hard to read, but basically what you're seeing is around a median forecast accuracy error of 0 distribution. And we've been able to shrink that and make it much more consistent with the new approach. And this is really positive because it involves a lot of savings for the solar farms, which we'll wrap up with at the end of the presentation. Now, it's really important to give consumers, the customers, excuse me, not consumers, the customers, access to this information in real time, because when you're submitting to an energy market, there's a lot of things that can go on. It's not just a solar forecast. So in this image here, I'm showing you a snapshot of our Solcast API toolkit in particular for our super rapid update customers. And so in this center part of the image are the live updating forecasts and accuracy graphs. You can see we have to keep track of the availability of the plant, any constraint that's in place, in addition to the forecast, the incoming measurements, and also show what we've actually submitted, what the forecast was, and compare that against the in-house model from AEMO. And this is really important for not only assessing forecast performance, but checking the uptime of the service, getting it all this information in one place, because this is actually fairly disparate information. It sits in a lot of different locations. The other useful aspect of this API toolkit, and this is actually just shown for a simple rapid update solar farm, only updating every 5 minutes the forecast, we can actually show the 1 hour ahead forecast, the measurements, estimated actuals, all in one place, updating in real time. And again, this is really important for the customer to be able to understand how forecasts have been trending over time, and also answer anything that they might be curious about with the data. It also helps them out with debugging the Sky Imager. So you'll notice up here in the top right, we give them a real-time feed of the Sky Imager. All sorts of interesting things happen in the dusty red Australian outback, not just bugs, but dirty lenses, birds, bird poo, and all matter of interruptions in that Sky Imager feed, including telecommunications ones. So they need to be able to keep an eye on that, because it's going to be the local person on site who gets to go tell that bug to get lost. Now let's take a quick look with the time we have remaining at the outcomes. So we've seen about an 11% forecast accuracy improvement in terms of the mean absolute error relative to the Australian Solar Energy Forecasting System simple regression model with a range of 6 to 28%. That shows us about a 10 to 20K per month cause or pace factor, estimated for about just 10% of accuracy improvement. I have to emphasize this is a very complicated calculation. It depends on a lot of different characteristics of the solar farm, the local energy market, its connection, etc. The numbers here are simplifications, but we have to give those numbers to really express the value. And so we're looking at and developing a financial model that will make that process more easy. And we also have technology improvements that expect another 10 to 20% forecast accuracy improvement over that comparison baseline I mentioned earlier. So the technology is continuing to improve, and that is coming not just from the Sky Imager, but also the cloud and radiation modeling algorithms. So here is our penultimate slide. I've done a cost-benefit analysis. Excellent. Just working great on time, and thank you, Eric and Tassos. Our cost-benefit analysis here does a simplification for you. We assume these numbers from a 30 to 50 megawatt solar farm, simplified FCAS, the Sky Imager is paid for up front. There's a maintenance. Maintenance is completely not included, and it's based on current solutions providers that we know in the space. And so I've put here 4 cases, the percentage improvement based on the previous slide, an estimate of the cause or pay factor that be saved based on a 10% is $10,000 saved, which is based on those real simplified numbers, and then some information about service costs and Sky Imager costs, and then calculated a return on investment horizon in months, and then the operational expenditure that would actually be saved over 1 year. So in these first 2 cases, they reflect where our company is trying to sit in the market in terms of low-cost Sky Imagers and relatively scalable low-cost monthly service fees. These give you a no-brainer decision. You can pay back this upfront cost in a month or less, and your OPEX saved, you can see in case number 2, you end up with about the best number you could ask for here out of the scenarios, $220,000. As you move toward more expensive Sky Imagers, you see increases in the service fees charged and the complexity of the hardware. That pushes out the return on investment, and really your operational expenditure starts to trend back down. So we seem to have exposed that the lower cost Sky Imagers that can give us some improvement can give us the better operational expenditure outcome.
Thank you.
That's important for the solar energy market. I'll end there and leave it open for any questions. Thank you.
Thanks, Hank. Eric, please, let's open the floor to questions now.
Yeah, great. Thanks, Nick. Great presentation. I think I saved one of the questions from Nikki earlier about how often we refresh the solar forecasts. Nick, I think you addressed that pretty nicely with super rapid update. But maybe you could also address other refresh horizons that might be of interest to users of solar forecasting.
Yeah, that's a great question. So I'll go more general with that approach in answering it. We have a few different tools that we rely on in solar forecasting, and moving forward in the time horizon from the start, really real-time power output measurements and Sky Imagers are the shortest update cycle. We can be getting data every few seconds, every few minutes. As you move out ahead of that, you're getting data from satellites every 5 to 15 minutes, depending on the region around the world. You can use the update to do the forecast update. And then as you move forward, you have weather models of various horizons, and the global models, which are the most widely available, are updating approximately every 6 hours and giving you 1 hour to 3 hour resolution data. So those are the opportunities to bring in the latest data to update the forecast. And you can also see that that means you can be updating the shorter term forecasting, nowcasting horizon more frequently than the several hours to day ahead, 7 days ahead forecast horizons.
Great, thanks for addressing that question, Nick. I see, Rodrigo, you've been answering some private questions in the chat. I hope others can see those. I thought maybe we could just bring up one of them that looks interesting to discuss as a whole. Jeff Lerner asks, does the value of forecasting go down when there is widespread adoption of distributed generation and load? So thinking about rooftop solar and charging stations, and the smart management of those distributed generators. Rodrigo, I know you answered that, but I thought that might be useful for the whole.
Yeah, sure. So if I could further comment on that, I really believe so the further deployment of more PV generation at the low voltage value will not reduce the need for solar forecast. It will actually increase the need and in a more diversified way, because we can see a bunch of different applications like scheduling my EV charger, for example, my electrical vehicle charging in terms of my PV generation. We can see the grid operators needing for a better control of the low voltage grid, and that will really require not only higher resolution in terms of time for solar generation, but also finer spatial resolution. And so surely Nick and Tassos can complement a bit on this, but I really believe that we'll start needing more focalized and niche kind of forecasts once the behind the meter or low voltage level starts growing.
That's a good answer, Rodrigo. And I can actually expand on that using a real world example. So in Australia, we have the bottom of the country called the Great Australian Bight. Looks like a big bite when Cookie Monster came and we had a chunk out of Australia. At the center of that is a state called South Australia. And in South Australia, the largest single generator in the state at 1.3 gigawatts is rooftop solar. And when you look at the utility scale solar and utility scale wind and put those three components together, often we have negative power prices, the entire state having its renewable energy provide the demand for the day, but that also comes and goes a lot. And so as you have that really large distributed solar resource in tandem with about 40% wind capacity in terms of generation in South Australia, what becomes important is not just distributed solar forecasts, but also those wind forecasts and on short-term horizons to make sure that supply and demand are balanced, and the case for renewable energy nowcasting and demand forecasting that includes rooftop solar, that actually increases in its importance in terms of its role in driving energy market decisions and system awareness. So as you get to those high penetrations and those rise across a different portfolio of renewable resources, including rooftop solar, we actually get off that linear trajectory, I think, of the importance and onto a nonlinear one in terms of the role and the value of those forecasts and how important it is to have them be very accurate because they drive system operations more intensely.
My view is that the value of accuracy of the forecasts may decrease as we have other ways to essentially take on variability. But forecasting the variability itself will be quite important as, for example, you need to know the coming volatility of the irradiance to optimize the dispatch schedule for your energy storage, for example, right? When we talk about electric vehicle integration with the grid and similar situations. So I think on a holistic sense, the value of forecasting will increase because more markets will require its results. But my personal view here, and I have to stress that, is that it will not be so much, a race after the highest accuracy in time. But I believe, if you're able to forecast the type of volatility you're going to get in the next, 15 minutes or 1 hour, that will help you make the best decisions in a variety of applications.
Thanks, all of you. we have another interesting question here.
Let's take one more question, Eric, since we're...
Yep, just one more. Yep.
Yeah.
Nick, maybe this is best for you to take a crack at. Viviana asks, what kind of algorithms are you using in the field of supervised learning?
That's a great question. I'll answer it more generally based on my experience with Viviana. The regressive approaches are the most common approach that is referred to as statistical or machine learning. However, I think that doesn't qualify for what we would call supervised learning. And we've seen a number of different methods be applied across the field. Neural networks are very popular, as are SVMs, or support vector machines. And both of those tools have promise. The neural network approach tends to be a bit more black box and less well understood, whereas support vectors come down to really intelligent feature selection, and the actually filtering of those features is where there's a lot of gain to be made. On our end, the machine learning that we run is based on creating unique PV power models and tuning those PV power models, and that actually can be based on regressive approaches and succeed quite well. But they're not actually producing the forecast. They are producing a unique profile that matches up with the solar irradiance forecast. In the forecasting space, looking at satellite imagery, supervised learning can actually be used in a computer vision sense, where we can use the satellite observation data to be the ground truth for the forecast.
Thanks, Nick. So thanks, Eric, as well. And I think it's time to wrap it up. So I'd like to thank all our panelists for the great presentations and discussion today. Thank all of you for your participation as well. And it's been a quite interesting and wide-ranging session. And I think it's provided some food for thought for all of us going forward. For those of you concerned about the webinar withdrawal symptoms, ISIG has you covered. So I'd like to remind you that there are 6 more technical sessions that will be held during the remainder of the month. You can find the full schedule of the upcoming sessions on the ISIG website, and you're all invited to attend. The next session is on forecasting R&D, and will be held on this Tuesday, June 6th, on next Tuesday, right? June 16 at 4 p.m. Eastern Daylight Time. Thanks again for the participation. Stay safe, and we all look forward to seeing you then. Bye-bye.